let's discuss something called polar covalent bonds. Polar covalent bonds. You learned about covalent bonds, but this idea of a polar covalent bond is something new. So let's take a simple example of a covalent bond. Let's do maybe something simple to start with, right? Let's do something like water, H2O. Okay, so let's think about a water molecule, H2O, and there's the formula for it. It could also be called dihydrogen monoxide, if we wanted to call it that, using our standard nomenclature rules, but a lot of chemicals have common names like this one, so we don't call it dihydrogen monoxide, we call it water. Let's try to draw the Lewis picture of what this would look like. And so it's an oxygen molecule sort of in the middle. And if we draw oxygen's electrons in a Lewis picture, there's two spots where oxygen needs to share, right? And if we draw hydrogen sort of here, it has one electron. We can see that these two sort of electrons that are lonely, they can form a pair if they share them between each other. So we get these two shared pairs. And so what we draw, getting dots all over, static. What we draw is the O here, and then a bar to show the shared pairs, like this. And then we have the other dots sort of left over that didn't get involved. So there's our Lewis picture of what the oxygen and hydrogen look like when they're joined together to make water. Now, let's look more closely at this sharing of pairs, these blue circles that I drew over here. There's more than one way to share. And some of you, when you were in kindergarten, may have noticed this. You may have noticed that sometimes, if you have two people playing ball, okay, and they have a little ball here, and they pass the ball sort of back and forth, you know, and they throw it back and forth. The ball is in each person's hand for about the same amount of time. We call it a fair sharing, right? Fair game. But imagine what would happen if you had a basketball, let's say, and this person here and a person over here, right? So this person passes the ball over here, and this person catches the ball. And instead of passing it back, this person begins to bounce the ball up and down, and they run around and they do some dribbling. They go way over here to the net, and they decide to take a shot all by themselves. And the other person is just waiting, and then they come back and they dribble over here. And then after a few minutes, they're like, okay, here, you have the ball, and they pass it back. But immediately after passing it back, they demand the ball again. This poor guy over here doesn't get a chance to do anything. He gets to do two bounces, and then he has to give the ball back to him. And then he plays around for a while, bounces. That would not be a fair sharing of the ball, would it? He'd be hogging the ball, and we would get upset about that. Well, it turns out that when atoms share their electrons, like this up here and here, they often share in a way that is unfair. They don't share evenly most of the time. They can share evenly like this in certain situations, but most of the time, there's going to be one who's hogging the ball more than others, or the electron. And so we have to describe this tendency to hog electrons. It's got a big fancy name. It's called because it has to do with electrons, negativity. That's a very important word in chemistry, electronegativity. And basically what it means is how hard atoms hold on to electrons, right? Or some people describe it as, the desire to have electrons. And so If you have, I'll move that up. If you have high electronegativity, if your electronegativity is high, what that means is you will tend to grab electrons like crazy. You are an electron hog. Negativity. That corresponds to holding on tight. Okay? I'll put the word hog over here to remind us. We call them a hog if you're taking something longer than you should. If your electronegativity is low, then you don't really care so much. Electronegativity low means that you less hold. It's very easy for somebody to come and steal the ball from you. Less hold on electrons. Okay? Less hold, which means you'll give them away. Now, how do we know which atoms are high and which atoms are low? And which ones are in between? It turns out that all the atoms on the periodic table sort of have their own little desire or their own electronegativity to grab onto or steal or hold or hog electrons. And of course, it has to do with the nature of the atom itself. Because remember that every atom is a nucleus with positive charge and electrons, negative charge, that are sort of buzzing all around the outside. But we have to remember that some atoms have 4 electrons buzzing around and 4 protons in the middle. Some have 8 or 10. And the more you have, the more they stretch out. So if you're a big atom, your electrons are buzzing around, but they're buzzing around way over here, way outside, far away, because there's no room for them all to buzz in close. And so that means that these little electrons that are way out here on the far away from the nucleus in a large atom, those can be grabbed more easily than, say, if you're a small atom and you've only got a couple of electrons floating around. They're all going to be floating around nice and tight to the nucleus, so you're not going to be able to grab those away as easily. Right? Makes sense. It's kind of like, these guys are just wandering a little too far away because there's no room for them in close. And so some other atom could come along and steal them quite simply, or much easier. So bigger atoms tend to have lower electronegativity than smaller atoms. So that's the first thing. Bigger atoms have lower electronegativity than smaller atoms. You might want to write that. Write that down. Okay? Bigger atoms tend to have lower electronegativity than smaller ones. Okay, so what that means, if we look at the periodic table, I'll just do a rough sketch of the periodic table here. There it is, okay, with all the atoms in it. Obviously, the more electrons you have, the bigger your atom will be. And so if you go down the periodic table towards the bottom, you've got very large atoms, right? Very, very large atoms. Like if we go down to the bottom and we see lead, lead is way down here at the bottom, lead. And lead has 82 electrons, 82 of them. So you can imagine, if this is the nucleus, those 82 electrons are going to be way outside of the lead, 82 of them. It's going to be a very big atom with a large cloud of electrons. But if we go up to the top and look at something like nitrogen, it's way up here. Well, nitrogen only has 7 electrons. So when you look at nitrogen with its 7 electrons, if this is the nucleus, those 7 are going to be sort of gathering closer in because they can squeeze in tighter to the middle. Remember, electrons repel each other, so they can't all squeeze in the middle or squeeze in close. They have to spread out the more there are. So these electrons would be harder to pull away because they're closer to that positive nucleus, which is attracting them. Whereas these ones down here are further away. So generally speaking, we say that as you go higher in the periodic table, you get more electronegative. You have more electronegativity. Nitrogen will hold on to its electrons more than lead will. Makes sense, right? Makes sense. The smaller you are, the closer they are, and the more you'll hold them. So that means you have higher electronegativity. So anything that's higher in the table will have more electronegativity than anything that's lower in the table. Okay, now there's also a sideways thing that happens on the table. Let's draw another table. Let's look at it just in general. Here it is, okay? If we look at something way over here like lithium, there's lithium. Well, lithium, if we draw his picture, I'll do it here. He's got a nucleus, maybe I can get a thinner line, and he's got 2 electrons, right, in the first orbit, but then he's got a total of 3, so I think he's got 1 more, like this, in the outer orbit, right? Okay, well, that one there has to go above. It has to go outside, so it's in a further orbit. It's further away. It's been pushed. Remember, only 2 can squeeze into any orbit. So he's pushed out there, and look what happens when you go across the table after lithium. If you go over here, you get to boron, right? Boron, and then you have nitrogen, and you have oxygen, carbon, sorry, I missed carbon. Let's not forget about carbon. Carbon, nitrogen, oxygen, and then you get over here, fluorine. And then, of course, neon at the end, but we don't worry about neon because its orbit is already full. Look what happens. To make boron, we have to add another electron here and make this a 2 to get, beryllium. We forgot beryllium over here. There's beryllium on that side. So that would be beryllium with 2 electrons. And then we have to add another electron to make boron. So then we have to make this 3 out here in the outer orbit, right? 3. Well, then to get carbon, we have to add another electron, so that becomes a 4. So you see what happens is we're only adding electrons into the same orbital. Because remember, that second orbit has an S and 3 P shapes, so we can hold up to 8 electrons. And if we go all the way across carbon, keep adding, when we get to neon, we find that we've reached 8. There are 8 electrons for neon, and it's full. Which means after neon, any new electrons have to jump down to the next row. Right? And that's why the atoms get bigger as you go down. Because the next ones would have to go way up here and start a new row. The rows of the periodic table correspond to the energy levels of the diagrams. Right? The very first row, which has hydrogen and helium, describes the electrons going into the first energy level. The second row describes the electrons going in here. And there's 8 of them because of those extra P shapes at this level. And then, of course, as you go down, you just keep adding levels for each row. But what happens to the shape or the size of the atom as we go across this row? That's what we want to find out. So let's think about it. Let's go back to lithium. Let me get my narrow line here. Let's go back to lithium. I'll draw a picture over here with his 2 electrons and then 1 electron. Now remember, there's also 3 positives in the nucleus that are pulling. I'll put a plus in here. It's pulling, right? And so if you add another electron in that orbit, it's going to be able to stay close, isn't it? So let's look at this one. Here's the next one. 2 E's, 2 E's. Well, what happens here is, because they're able to fill the same orbit, they can stay relatively close. And what that means is the positive charge that's attracting those and the negative charge, you've increased it. Now it's 4 and 4. So it's pulling a little tighter instead of over here where it was 3 and 3. So what happens is lithium tends to be a little bit bigger because his electrons are in that that sort of first and second level. But then when you get to beryllium, beryllium has a slightly stronger pull, and so his electrons get tucked in a little bit closer. And when you get over to boron, boron is pulling now with 3, actually I should say 5, right? 3 in the outer orbit, but 5 altogether, and the 5 protons, which causes the shell to shrink even more. So what happens is, even though you're adding an electron each time, the size of the atom is shrinking because you're adding an electron in the same orbit, which allows the positive charge to sort of pull that orbit in tighter because you're increasing the negative charge in the orbit. And so what happens is the atoms actually get a little bit smaller in size as you go to the right across the table, as you follow this arrow this way. And if they get a little bit smaller, that means they get more electronegative. Boron is holding on tighter to his electrons because they're tucked in closer than lithium is. So that means we have another little sort of rule or trend on the table. As you go from the left-hand side over here to the right-hand side across the table, electronegativity increases. Electronegativity increases from left to right across the table. So what that means is that if you have a table like this, we have 2 rules. I'm going to summarize both rules now. Okay? What that means is we've already seen that if you go up the table, that's the increasing electronegativity. But now we also can draw another line across the table. If you go this way, that's increasing electronegativity. Okay? So you have to use the 2 together, which is interesting. So what that means is that we can find the atom that has the most electronegativity if we go as high as possible and as far to the right as possible. Now remember that our little noble gas friends, I'm going to add them over here. There's, helium, neon, krypton, argon, radon, xenon, all those guys. They're not involved because they don't have any desire to get electrons because they are full. So we're ignoring the noble gases on the far end. So who then sits right here? Who is the highest and the most to the right of all the elements? If you look on your periodic table, it's fluorine. Fluorine. So F is the most electronegative element. Fluorine is the biggest electron hog in the world, and it will grab electrons from just about anybody whenever possible. Whereas, if we look at the opposite side of the table, if we go as far to the left and as far down as possible, we see the lonely little francium down here. It's funny how one is F and one is FR. All down there at the bottom. Francium is the least electronegative, which means francium will give its electrons away to anybody. All you have to do is walk by and make a gentle breeze, and you can knock electrons off of francium. It has very low electronegativity. Now, of course, this is a general rule, but when things get tight, close together, it's hard to tell. So, like for instance, if we were to look at our table and we were to look at 2 others, let's say we were to look at oxygen, which is here, and then we were to look at phosphorus, which is sort of diagonal right here. Well, in this case, we could say, well, oxygen is higher, right, than phosphorus, but it's also further to the right. So it kind of wins both ways. So oxygen must be more electronegative than phosphorus, right? Because it's higher and it's more to the right. But if you look just past phosphorus and you get to chlorine right over here, we got a little bit of an issue. Oxygen is higher than chlorine, So you'd think that that would make it more electronegative. But chlorine is more to the right. So which one wins? Is chlorine, does the being to the right trump being on top, or vice versa? When you get close like this together, it's not as easy to tell. And so what we have to do is we have to actually measure these atoms' electronegativity. And we have done that, and we have special numbers that you can find. Some periodic tables will list the electronegativity number, but not a lot. Usually you have to request or Google a special table that shows electronegativity numbers. And when you get into higher chemistry in grade 11, you'll learn those numbers and how they work. We don't really care. We just want to be aware of the fact that there's a different pull of electrons depending on where you sit in the periodic table. That's the very important thing that we need to understand. And it has to do with how tightly you're holding the electrons, which has to do with the size of the atom. And it gets bigger as you go up and bigger as you move across to the right. That's the trend we want to remember, okay? Okay. So then what does this mean for the sharing of atoms in a covalent bond? Let's go back to our example of water from the very start. Let's take our water. There it is. And the little bars represent the shared pairs, right? In that little bar, one electron came from oxygen and one came from hydrogen. But guess what? If you look at the periodic table, we see where oxygen is here. Hydrogen is way over here. Far, far, far to the left. Which means oxygen has more electronegativity than hydrogen. Even though hydrogen's a little bit higher, it's only one level higher, but it's about 6 or 7 atoms way over to the left. So that's an obvious one, right? Oxygen is more electronegative, which means oxygen will hog these electrons. So if we just imagine where these shared electrons are going and what they're doing, well, in this particular pair right here, they're not bouncing back and forth nice and evenly. It's more like this. It's more like the oxygen has them both over here. And every once in a while, hydrogen gets a share. But most of the time, they're being pulled over close to the oxygen. And it's a very uneven kind of sharing, right? They spend most of their time over here, and only once in a while does hydrogen get them for like a very short time. That's not equal sharing. That's unfair sharing, isn't it? Okay. Now let's remember one more thing about electrons. They are negatively charged. So let's examine again what happens when we have an O bond and an H bond, right? Well, an O has a nucleus with protons in it, and the H has a nucleus with protons in it. Now remember, before they shared, they had the same number of protons and electrons. All the atoms do, right? The atomic number, which means there's an even balance. But as soon as they share, it changes the balance. So if all these electrons, if this little electron right here that is supposed to be shared is spending more time over here because oxygen is hogging it, right? And only one or two times. Oxygen is hogging it. That means there's an extra electron, which means there's more negative on this side. More negative. Hydrogen's electron is over there. And then if you look over here on this side at poor little hydrogen, he's just a little plus proton, and he hardly ever has an electron, which means this part is now less negative. So we get an imbalance of that electric charge. Wherever the electron is being hogged, there is more negative charge. What this is called is a polar bond. Polar means instead of being nice and spread out even, you've got two opposite sides. Right? The Earth has a very, very definite North Pole and South Pole. Of course, it doesn't have an East or West Pole because as it spins around, It's all spread out. But it does have a distinct difference. So a polar, all that means is two opposites, right? Two people with opposite personalities could be considered polar opposites. You'll sometimes hear them say that, right? So all polar means is two different things. And the thing that's different here is the electric charge because of the electrons that are being hogged. So what we say is that the bond between oxygen, oops, let me write that better. The bond between oxygen and hydrogen is polar. And what that means is that oxygen hogs the electrons more. The electrons in the shared pair more, and is more negative. Now we have to be careful here because it's still sharing, even though it's not perfect. This is not an ion forming. In the very first lectures, we talked about how lithium would give its electron to fluorine entirely, and fluorine would become a negatively charged ion. Remember that? And sodium would become a positively charged ion. Okay? So when sodium and fluorine get together, there's an electron that's transferred, and it stays there. It doesn't bounce back and forth. It's not shared at all. Sodium never gets it back, not even for 5 seconds. That's a different story than an electron that would, like with hydrogen and oxygen, an electron that is shared, but it's mostly here, but it still does get a chance to visit the hydrogen every once in a while. You see the difference? So this is a sharing, but it's an uneven sharing, and this is a complete giving. Well, you have to ask the question, at what point does uneven sharing turn into completely giving? If you were playing catch with your friend and you got the ball 1 minute and they got it 7 minutes, that's pretty unequal. What if they got it for 1,000 years and you got it for 1 second? Well, they may as well just have the ball, right? So there's a fine line here between what we call a polar covalent bond on this side, one where there's sharing but it's unequal, and then a complete giving and taking, which we call an ionic bond. And next year, you're going to learn that we can use the electronegativity numbers or values of each, and we can look at the differences between them, and we can determine whether or not the bond will be a complete sharing, or a polar sharing, or actually an ionic bond. But it is a fine line, isn't it? So we have sort of this sort of spectrum of possibilities. Now, if we look at the polar covalent bond, what we do is we write, here's the oxygen, and here's the hydrogen, okay? And then we also have to look at the other one that's happening down below. Everything I described for the one is also happening for the other. So let's think about this. What this means is that the electrons, we can sort of imagine an imaginary line through the molecule like this, and the electrons in those two shared bars are spending more time over here on this side with the oxygen. What that means is the oxygen has a little more negative, and so we use a symbol. We don't want it to look like an ion, so we use a symbol, a little sigma, a little Greek S, a sigma symbol, and then we put a little minus to show that over here, that's where the electrons are hanging out, and that side is a little more minus. It's a little more negatively charged because all the electrons are being hogged there. On the other side, over here, where we have no electrons hanging out hardly at all, because they're being hogged, that leaves us with a sigma plus, or a positive little bit of a charge. Okay? Okay, so this is the essence of the polar covalent bond. Now, so just to kind of recap, simply put, what you do is you take any bond. You can take carbon bonded to nitrogen. and you look at the periodic table and you try to determine which one is more electronegative. So on the periodic table, carbon is right here and nitrogen is right here. Carbon, nitrogen. So nitrogen is a little more to the right, which means it's slightly more electronegative, which means that the electrons will spend more time around nitrogen than they will around carbon. Nitrogen will hog them a little bit. Now, this is a very light polarity because they're so close together. The closer you are on the table, the closer your electronegativities are. And so here, there wouldn't be as strong of a difference, but there would be a slight difference. And what we could say is we could write on this side of the bond, a sigma with a minus to show that the electrons are being sort of hogged there a little bit more than they are over here. And we can use numbers to determine how strong these polarities are, but we just want to learn the concept for now and just understand that there's a slight difference. Because they're so close together, this would be a very slight difference, as opposed to what we saw over here with the hydrogen and the oxygen, because they're so far apart. The farther apart you are, the stronger the difference. That's why when you get way over here and you start pulling against over here, you tend to get almost a complete pull, right? You get the full ionic transfer of an electron. But with the covalent compounds here in this part of the table, we have to use the trends that we've talked about to determine who's more electronegative. So we can understand that this is a polar bond. Now, that means that just about every bond you find will be somewhat polar because everybody's a little bit different, except for the situations where you have the same atom sharing with itself. For instance, in the O2 molecule, oxygen shares twice with itself to get something that looks like this. Now, because oxygen is on both sides of the bond, well, oxygen is the same oxygen. So what happens here is a very equal share where nobody seems to hog it at all because they're the same person essentially, right? The same atom with the same electronegativity. So this would be the only place where you would get a non-polar covalent bond. When you have a bond between two of the same atoms. Okay? So essentially then, when we're talking about bonding so far, what we've seen is there's the ionic bond, which is really the complete giving and taking. Okay, so I'm going to put complete giving and taking. And what happens then is you form ions. So you get lithium, and he forms a positive ion, right? Plus, and say oxygen forming a negative ion, 2 minus, and so on. And that's complete give and take. There's no share at all. And we have a set of rules for that. But on the other side of this chart, we have the covalent side, but it seems to be divided into two, right? There's the sort of, over here I'll put the equal sharing, which would be like two of the same atoms, like we just saw, atoms O2, oxygen binding to oxygen, right? No hogging because they're both the same. But then in the rest of it, we have this sort of spectrum that goes from, we call it polar bonding, which is still covalent, but it goes on a scale. And of course, here you have high electronegativity difference on the left side, say, and then on the right side of that, you have very little. So let's just write over on the right-hand side, there would be weakly polar bonds. They're almost the same as equal sharing because the difference is very, very low, right? So I don't know how, I can't fit much more on here, but if we think about electronegativity difference, the difference between them how far apart they are on the table. These would be very close together with little difference between them, a low difference. Whereas over here, where you have a high difference, you have what would be called strongly polar bonds. So they're almost ionic. The sharing is so unequal that it's almost like a giving and taking, but not quite. So it's still part of the covalent world. So this dividing line right here is very important. And we have a mathematical way of determining this dividing line, but you'll learn about that next year. All we want to do is get the concept in our heads, because this is a very important part of covalent bonding. And in fact, most of the bonds will fall in this region. Most of the covalent bonds. It's only when you're with yourself do you get the equal sharing on the other side. All right. And so then, of course, we have to look at how each polar bond in a molecule is distributed to see what happens to the whole molecule and see how the positives and negatives are spread around it. And so that means that molecules can have what's called a polar nature or a non-polar nature, depending on how the bonds are shaped. Okay? And for instance, I'll just show you again water. It's very important. Water has, when you draw the Lewis picture, sort of you have an H over here and an H over here, right? Water has a definite side to it. There's a definite imaginary line here that separates the positive side, where the electrons are not most of the time, and the negative side, where the electrons are being hogged by the oxygen. And that's what we call a polar molecule. And this is what makes water so special, because it can do some pretty amazing things, as we'll see later on. But that, I think, is where we'll call it at the end of our polar covalent bonding.